Hello, in this video we will be covering Chapter 14, Module 13. The subject of the chapter is temperature and heat. This is the first chapter of a series of 3 chapters until the end of the year, where we will be covering the subject of temperature, heat, and the laws of thermodynamics. I'm hoping that this chapter is going to be easy for you because most likely you have seen most of the material in this chapter in your previous courses, especially chemistry, whether it's high school or college, and probably physical science courses in high school. Okay, so let's get down to it. We begin with the study of temperature. And as you all know, there are 2 famous temperature scales. One is called the Fahrenheit, and the other one is called the Celsius. And you're probably familiar with the equations, so let's get that. Let's go into them. So we have 2 scales here, 2 temperature scales. The Fahrenheit and the Celsius. The Fahrenheit, as you all know, is widely used here in the US. The rest of the world, pretty much, they use the Celsius. And there is a linear relationship that allows you to convert between Fahrenheit and Celsius. And the relationship is this. We have if Fahrenheit is equal to 9/5 plus 32. And if you want to convert from Celsius to Fahrenheit, you simply solve for C and you will get the following equation. C equals to 5/9 F minus 32. Okay, so an example of that, of course, remember F here for Fahrenheit and C here for Celsius. So, for example, the most common temperature that we all know is the human temperature. As you know, for a healthy person, the temperature is 98.6 degrees Fahrenheit. And let's say that I am interested in converting it into Celsius. And I hope you already know it. It's 37. It's a nice prime number. So let's see how we do that. So I have the Fahrenheit. I need to convert to Celsius. So in this case, I'm going to be using the second equation, C. So it says C equal to 5/9 F minus 32. All you need to do is just substitute it. So they're going to be 5/9 times the Fahrenheit, which is 98.6 minus 32. And then we would just calculate that. I would just use my calculator. So we have 5 divided by 9 times 98.6. And then you subtract 32 from it, and then the answer would be, that will be 37, right? Degrees Celsius. Okay. Another example is, let's say, for example, I know that the boiling temperature of water is 100 degrees Celsius, and what is it in Fahrenheit? And I am sure you know it's 212, so let's see if we get that. So we know that F is equal to 9/5 C plus 32. And you just plug it in, so that's 9/5. Multiply this by 100 plus 32. And when I calculate that, so I have 9 divided by 5 times 100 plus 32. And the answer is 212 degrees Fahrenheit. And so on. You get that? Okay. Another scale that is used heavily in science, beside the Fahrenheit and the Celsius, is the Kelvin temperature. Okay, the Kelvin temperature scale, that is. the Kelvin temperature scale. And it has the symbol K, capital letter K, and it's simply, you are converting Celsius into Kelvin, okay? Not Fahrenheit into Kelvin. You're converting always Celsius into Kelvin. If you're given a Fahrenheit, the first step that you need to do is to convert it back to Celsius, and then you convert it to Kelvin. Okay, that is a direct way to convert Fahrenheit to Kelvin, but that's how you do it. So if you're given a Fahrenheit, first convert it to Celsius, and then you convert it to Kelvin. And it basically, the relationship says is that the temperature in Kelvin, I'm going to call it T sub K, is basically equal to the temperature in Celsius plus 273.15 degrees Celsius. Okay, that's basically the formula for it. So, for example, if the human temperature is 37 degrees Celsius, what is it in Kelvin? All you need simply is just to add 273. So we have here 273.15 plus 37, and then we just add them up together, and that will give me 310.1 Kelvin. Okay. Here's a table for you that you should be familiar with the following temperatures, both in Kelvin, in Fahrenheit and Celsius. Specifically pertains to water. So if I make a table that looks something like that, where, let's say this is the boiling temperature of water, this is the freezing temperature, and let's say this is degrees Celsius, and this is degree Fahrenheit. The boiling temperature of water in Celsius is 100, and the the freezing temperature, of course, is 0, and the boiling temperature of water in Fahrenheit is 212, and the freezing temperature is 32. Okay. And for the human, we just said that for human temperature, it is in Celsius, and in Fahrenheit, it is 37 degrees Celsius or 98.6 degree Fahrenheit. Okay. Okay, good. Now we move on to the next topic in the chapter, and that is section 14.3, and that is the thermal expansion. Thermal expansion. What that means is that, as you all know, most materials, except water and some others, most materials expand when the temperature increases, and they contract or shrink in size when the temperature decreases. In other words, and this expansion is usually linear in nature. Okay, so for example, if I have a rod, here is a rod, for example. And let's assume that the initial length of this rod, we're going to call it L sub naught, and it is at temperature T naught. For example, I have this rod, and it is in the inside my room at room temperature T naught, you know, whatever it is. And then I take this rod and I heat it up, okay, or put it in the outside in the sunlight. Maybe the temperature is higher outside. So what will happen? The rod is going to heat up, and as a result of that, is going to expand. And let's assume that it will expand this much from, let's say, from here. It's going to expand just a little bit more, say somewhere here, like that. And now the new length of the rod is L naught plus delta L, where this delta L is the difference from here to here. So this is delta L, okay? So to measure this value, delta L, there is a formula, and the formula is basically alpha L naught times delta T, okay? Let me box this equation, I'll talk about it. So let's go back to the original rod. I have this rod, and it is at some temperature T naught, and there is the corresponding length L naught, and then I heat it up, and now it is at a new temperature T, okay, assuming T here is greater than T naught, and as a result of that, the rod's length will increase by delta L. You see what I'm saying? So this delta L is the increase in the length of the rod, the linear, what we call the linear expansion. Okay, this linear expansion delta L can actually be measured or predicted by this formula. It's basically alpha. Alpha is a coefficient, I'll come back to it in a second, times the original length of the rod at T naught, and then times delta T. What is delta T? Delta T basically is the difference between the two temperatures here, T and T naught, okay, in such a way that delta T makes sure it's positive. Okay, so you basically you want to put the higher temperature minus the lower temperature, so that's going to be T minus T naught, okay? So that will be the value delta T here, got that? Alpha here is called the coefficient of linear expansion, the coefficient of linear expansion. Okay, and it's just a number, it's a coefficient. You can actually look it up from the book. So if you go back to the book, and on table 14.1, page 431, and you'll see it right there. Let me magnify it a little bit. Right here, okay? So the coefficient of linear expansion, alpha, it has the unit either inverse Kelvin or inverse Celsius. Both of them are equivalent. You can pick whichever you want. So, for example, the linear expansion of steel is 1.2 times 10 to the negative 5. Copper, 1.7 times 10 to the negative 5. Brass, aluminum. And then you have nickel, ion alloy, INVAR, never heard of it. Quartz, 0.04 times 10 to the negative 5, and so on, okay? So basically, you want to look up the table for that. And I give you a word of warning. From my experience dealing with the coefficient of linear expansions and other tables that we're going to deal with this in this video, always refer back to your own textbook, the table here. So maybe you want to take a screenshot of this table and keep it on your desktop, and do not use the internet. If you look up steel, the linear expansion for steel on the internet, you may get a different number, okay? It's kind of weird. I don't know why is that the case. So please stick with your book, especially if you are working on problems at Pearson, homework or exam, and you want to get the right answer, because Pearson assumes that the table or the number that we deal with is the numbers that are in our textbook. So you may, like I said, the best idea is to take a screenshot and keep it in your desktop or something like that, or print it out and hang it on the wall or whatever. Okay, so anyway, that's basically what alpha is. So just a number that you look up. Let me give an example, and the example is actually from the book. It's the one below the table, this one here. It says here, let's start from here. It says a surveyor uses a steel measuring tape that is exactly 50 meters. Look at the significant figures. Those are just significant figures, 000. So he said 50.000 meter long at a temperature of 20 degrees Celsius. Okay, so you have a surveyor. He's using a steel measuring tape, and the measuring tape measures up to 50 meter long things. Now he's asking, what is the length of on a hot summer day when the temperature is 35 degrees? In other words, what will happen to this measuring tape, this steel measuring tape? It's going to heat up and it's going to expand in length, right? So we want to measure that delta value, this difference in them, okay? Kind of a simple problem, I hope. So all you need to do is let me write it down. So here, what's given to us is that the original length of the steel tape is 50 0.000 meters. Again, those three triple zeros are just significant figures. And then he says the original temperature, T naught, is 20 degrees Celsius. And he said the new temperature is, what is it, 35? I'm looking at the hard copy here. 35, yes. And we don't know the new length, okay? And he's interested in finding, or we are interested in finding the delta L. We can find the length later, but we want to find delta L. So basically, delta L is equal to alpha L naught delta T, okay? Now, here is the thing about, before I cover this problem, here is something about T. When it comes to physics, anytime you see a formula that contains temperature, okay, that temperature is always in Kelvin. You want to keep that in mind, okay? This is very, very important. You always plug in temperatures in Kelvin. Never plug them in Fahrenheit or Celsius, except under certain conditions. I'm going to tell you the little trick. But basically, by default, if you see a physics formula in physics where there is a temperature that you have to plug in, by default, you plug it in Kelvin. You have to convert into Kelvin. But here is the trick. Watch. See, I have the temperature is given to us right there, and I want to get delta T, correct? Well, first thing I need to do, like I just said, according to what I have just said, is that it has to be in Kelvin. So T naught is 20 degrees Celsius. So that means I have to convert it into Kelvin. And so I'm going to add to it what? 273. So it's going to be 273. So it's going to be 20 plus 273. And that gives me 293, correct? Kelvin. Now, the new one, or the other temperature, 35. And I just add it up. So 235 plus 273, and that gives me 273 plus 35, answer 308, okay? So I got here 308 Kelvin, correct? Now, what is delta T? Just take the difference between them. 308 minus 293. 308, sorry, minus 293, answer 15. 15 Kelvin. Is that right? Okay. What I have done here is absolutely correct. There's nothing wrong with it. But because it's a delta, not a T by itself, it's a delta, I can actually, if I take the difference between them without converting it to Kelvin, I will always get the answer, the right answer. In other words, if I just go with T minus T naught, where both are in Celsius, 35 degrees Celsius minus 20 degrees Celsius, this will also give me 15 degrees Celsius. You see that? So in other words, whether I convert or not, I will get the same answer only if and only if there is a delta. If there is a T by itself, you're supposed to plug in only a temperature T, make sure that that T is always in Kelvin. You got that? So it is safe to, if you're doing delta T, it is safe not to convert to Kelvin and simply just take the difference, and you will get the same answer, whether you could convert to Kelvin or not, okay? It's just a little trick for you. Anyway, moving on. So I have here alpha for steel, so I go back to the book, and I look up the table, and for steel, it is 1.2 times 10 to the negative 5. So I just plug it in. So I have here 1.2 times 10 to the negative 5, multiplied by the original length, which is 50, right? I can put those significant 3 zeros if I want to, times delta T, which is 15 Kelvin. And then we plug in all of that, and that will give me 9 times 10 to the power of 3 meters, okay? Or if you want 9 millimeter, okay? So what happened to this tape, this steel tape, it has increased by this much. So what is the new length? Well, the new length will be L naught plus delta L. Is that right? So it's going to be 50.000 plus 0.009. Now you know why those three zeros that are significant figures is because it will allow us to add up this 9. It's so tiny. So anyway, when we do that, and you'll end up getting that the new length is going to be 50.009 meters. Okay, got it? Okay, good. Okay, here's another one. This is from my own notes, and it's kind of a tricky problem. Imagine you have let's say a sheet, let's say a steel sheet, okay? This is a steel sheet. And let's say I make a hole in it here, a circular hole. I cut it out, and I have a circular hole. And then I measure the area of the circular hole, okay? So I have a circular hole here, and I measure its area, okay? And then let's say the area is some A naught. Now what I want to do, I heat up the steel. So sorry, let me go back. So it is some area A naught, you know, which is equal to pi r naught squared, right? The area of the circle, at some temperature T naught. Now here is the trick. If I would heat up the steel sheet, would the hole get bigger or smaller? Think about it. See, if you heat it up, that means this whole area is going to expand. So it's going to expand in this direction, like that. Here, 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 like that. Look at that. So is it going to shrink in size, or is it going to expand in size? It's kind of a brain teaser. But anyway, we can. This is basically the example that I want to work on. It's not in the book. This is from my own notes. So the question is, does the hole get bigger or smaller? Okay. All right. Before I do this problem, so let's go back to the formula that I have just covered. We said that for linear expansion, we said that if I have a linear object that is elongated, such as a rod or a measuring tape or something like that, so the expansion, if I want to measure it, it is alpha, the expansion coefficient, times the original length times delta T, the difference between the two temperatures. Now, if I have an area, okay, say for example like the surface or the steel sheet here, okay, you can actually use the same formula, except it is adjusted for the area. It becomes like that. Delta A equals to gamma L naught. Hold on, I want to make sure your book uses gamma, not beta. I'm sorry, 1 second. Yes, gamma. Gamma A naught, not L naught, sorry, times delta T. What that means is that A naught here is the original area of that surface, okay? So this is for surface expansion. Okay, and delta T, of course, is the difference in temperatures. A naught is the area of the surface, the original at T naught. And then you have gamma here is the coefficient of surface expansion. But this gamma, it's really simply what? It's actually 2 alpha. It's really that simple. In other words, if I know alpha, which is the coefficient of linear expansion, gamma is you double it or multiply by 2, you will get the coefficient of surface expansion. Why is that? Well, because if you have a, let's say you have a sheet like the one I draw above, and if it is going to expand, it's going to expand in this direction and in this direction. So it has 2 dimensions. One, each of them is an alpha. You see what I'm saying? So the total here would be 2 alpha. Get that? So that will be for the surface expansion. So there is a table. I believe your book has a table for the surface. It doesn't actually, but anyway, you can, if you want to know that gamma, simply take that alpha and multiply by 2 and you will get the gamma. There is another formula for the volume expansion, which means, let's say I have a block of say let's say I have a block of steel, for example, like that, okay? Three-dimensional block of steel. And I heat it up. So it's going to expand in 3 directions like that. You see what I'm saying? And so this is volume expansion. So delta V in this case is going to be equal to, again, your book uses beta V naught times delta T. What is beta? The beta is the coefficient of volume expansion. And it is in your book on page, table 2, on page 432. Let me show it to you. Keep in mind the steel 1.2. I'm going to show you. If I multiply this by 3, I will get the volume expansion. Right here, okay, the coefficient of volume. He doesn't put the area, I'm not sure why. But anyway, so he calls it beta, and there they are. For example, look at the steel. The steel is right here, this number right here, 3.6. Well, what is 3.6? The original for the linear is 1.2. When you multiply 1.2, multiply this by 3, you will get 3.6. See that? So all you need to do, you don't even need the stable as long as you have the linear expansion, alpha. Simply just multiply by 3. Again, for the surface or area, you multiply by 2. For volume, you multiply the alpha by 3. It's that simple. You got it? Okay. So going back to our problem, let me box those equations. And so going back to our problem here, it says that does the whole, so we have this, again, let me just review it very quickly. So I have a sheet of steel, there is a hole in there. The area of this hole at temperature T naught is A naught. And of course, A naught can be measured as pi R naught squared, the radius squared. And now I heat it up to a new temperature. The question is, would it get bigger or smaller? And if we have numbers, what is the new area? You see what I'm saying? Okay, so how do we do it? Let me just skip all of that and come here. I'll just come here, sorry. So he says, let's say that the area A naught, we have some numbers here. The area A naught is 100 centimeters squared, is cut in a piece of steel at 20 degrees Celsius. What is the area if the steel sheet is heated to 100 degrees Celsius? That's the boiling temperature of water, right? So if it is heated to 100 degrees Celsius. So what we do, simply you go back to the area, which is the surface expansion right here, and I'm going to write it down. So here we have delta A is equal to gamma A naught times delta T. You see what I'm saying? So what is gamma? Gamma is 2 alpha. Again, the table for area is not given to us, but again, it's not difficult. All we need is to go to the alpha, multiply by 2, because area is 2 dimensions. So we go 2 times 1.2 times 10 to the negative 5. And then when we calculate that, it'll be what? 2.4 times 10 to the negative 5 Kelvin per Kelvin. And then we would just calculate that. And so delta A is equal to, again, let me just emphasize, so that's 2 alpha A naught delta T. So that will give me 2.4 times 10 to the negative 5 times the area, which is 100. I want to convert it to meters squared, so that's going to be 100 times 10 to the negative 4 meters squared. Multiply that by the difference in temperatures. again, like I said, you can convert to Kelvin and take the difference, or just take the difference directly. You're going to get the same answer. So they're just going to be 100 minus 20. And then we calculate all that. And when you do so, you will end up with delta A equals to, let me do that. I hope you are calculating with me, times 100 minus 80. And answer, I got 1.92 times 10 to the negative 5 meters squared, or 0.192 centimeter squared. Okay, there we go. Okay, so I want to answer the question now. Go back to the original question. Does the hole get bigger or smaller? Well, look at that. We have a positive delta A, so it will get bigger, actually. By how much? By this much. Okay, so hole gets bigger. Okay. I mean, let me just go one more step. We can also say, what is the new area? The new area would be A equals A naught plus delta A. So that will be 100 centimeters squared plus 0.192 centimeters squared. And then when you calculate that, it'll be 100.192 centimeters squared. As you can see, it's bigger. Okay. All right. The next topic, heat energy. That's section 4. Please take the time to read this, at least the first page of that section. There is a lot of text that you need to understand. Let me just show it to you very quickly. It's on page 35. Please take the time to read this content right here, heat energy, all of that. And then here he starts talking about different units for energy. We're going to go over them right here. So let me talk about those. Again, the notes that I have directly out of the textbook. So first of all, we have the definition of what is called the calorie. Now remember, the word calorie here is different from the food calories. Okay, there are two. They're not the same. You have, when you buy a food item, say cheese, and you look in the back for the nutritional thing, the ingredients and all that, and you see that certain, the word calorie there. Those are food calorie, and food calorie is different from the calorie that we use in physics. Now, the calorie that we use in physics, which is a unit of energy, and it is a small letter C, so it is it's kind of hard to draw a small letter and a big letter, compare them. But anyway, calorie, and this is a small letter, and then you have big calorie, which is a big letter here, capital letter. The big calorie is the food calorie, okay? The one that you see in the back of, any food item you buy. That's the food calorie. And the food calorie, this big C, let me put a line there to indicate it's a big C. So this 1 calorie, food calorie that is equal to 1,000 energy calorie, the small c. You see what I'm saying? That would be one way to convert them. In other words, the food calorie, big C, is equal to 1 kilocalorie. Okay, kilo for 1,000. Okay. In this course and in physics in general, we never use the food calorie. So when you read the word calorie in any physics textbook, in our textbook, by default, just assume it is the regular energy calorie, okay, as an energy, not a food. We don't deal with food. This is not a nutrition class. So we never deal with it. So don't get confused here. We just don't deal with it. But this is just general. You know, when you see it in capital C, at least in physics, I'm not sure how they do it in other sciences, but the capital C, it's a food calorie, and the small letter c is basically the energy, the measure. It's just another unit for measuring energy, like joule and so on, okay? All right, so 1 cal, again, we're talking about energy here. 1 cal for calorie is equal to 4.186 joule, okay? This is an important conversion unit. 1 kilocal, 1,000 calorie that is, it's 4,186 joule. Okay, you can see that, I guess. And then there is another unit that is common, especially when you buy a refrigerator or an air conditioner. You will see it right there on the back of the device, such as, that you'll see it in the back of the refrigerator or the air conditioner, and that is the BTU. BTU, and it stands for British Thermal Units, okay? British Thermal Unit, the BTU, and this 1 BTU is equal to 252 calories, or 1,055 joule. Again, we're probably not going to see it at all, but just be familiar with it, because you see it a lot when you buy any devices for your home, household items that give off heat. You see what I'm saying? Such as refrigerator, stove, and oven, and microwave, and all of that. They measure it in BTU, and the definition of the BTU is the amount of heat requires to raise the temperature of 1 pound of water by 1 degree Fahrenheit. It's not important, but that's what it is. You can look it up if you're curious. Okay. Now we come to another topic that I want to talk about, and within the section, before we start doing problem, and that is the specific heat. This is a very important topic, the specific. And I believe if you're doing labs this year, there is an experiment where you have to calculate the specific heat of a certain material. Maybe you've done it already, I'm not sure. Okay. So what is the specific heat? The specific heat is the quantity of heat energy that is required to raise the temperature of a mass, of a material mass, of a substance, of a mass of a substance from T1 to T2. Okay? This is the specific heat. I'll give an example. In other words, a specific heat is different for each material, for different material. In other words, the specific heat of for wood is different than, say, iron. Copper is different from silver. Gold is different from aluminum, and so on. Okay, each material has its own unique specific heat. This amount of heat necessary to raise the temperature by a certain amount. Okay, here's an example just to kind of explain it to you. Let's say I have water. Okay, the mass of the water is 1 kilogram, and let's say that I want to raise the temperature of this water by 1 degree. Okay, just 1 degree Celsius. I want to raise that temperature of this water by 1 degree Celsius. The question is, how much heat do I need? It turned out that I need this much heat, 4186 joule, which is basically here it is right here, 1,000 calorie. Okay, so that's how the calorie is defined. 1,000 calorie is the amount of heat necessary to raise the temperature of 1 kilogram of water by 1 degree. Okay, now if I take, say for example, copper, that is exactly also 1 kilogram. So that's, and I want to raise this temperature also by 1 degree, just the same as water. You see the similarity between them? So I have water, 1 kilogram mass. I want to raise the temperature by 1 degree. How much heat do I need? 4,186 joule. Now, if I have say a block of copper of mass 1 kilogram, and I want to raise the temperature by 1 degree, do I need the same amount? No. All I need is 387 joule. See that? So I don't need a lot of energy to raise that temperature of copper, but I need much more energy to raise the same amount of temperature for, say, water. Why is that? Because each substance, okay, each material has its own specific heat. You get that? That's how what specific heat is defined as. Here, it is the quantity of heat or energy that is required to raise the temperature of a mass of a substance from T1 to T2. Okay, our example here by 1 degree, for example. Okay, so in other words, let me just write one more sentence here. Every substance has a unique value for mass of 1 kilogram and delta T of 1 degree Celsius. This is referred to as the specific heat. Okay? All right. There is a definition here for energy, and that is the Q value. Q here means the quantity or quantity of heat. So it's a symbol of energy, but specifically, and what kind of energy? Not potential energy, not kinetic energy, heat energy. Okay, so Q is reserved for that symbol, for that heat energy, Q. And this Q is equal to mc delta T. This is probably the most important equation in this chapter. Make sure you write it down and memorize it if possible. Okay, mc delta T. What that means? It basically means the amount of heat Q that is needed to raise the temperature by delta T for a specific mass of a substance, and of course that substance has a specific heat C. Okay? So what that means is that the quantity, the word quantity and Q, that's where the Q came from. Quantity needed to raise the temperature of a substance of mass M from T1 to T2, okay, is of course equal to Q. That amount, that quantity Q is equal to this. Okay. Let me, before I give you an example and show you how all that stuff means, let me show you table 14.3 on page 38. Again, stick with the table in your book, guys, when it comes to getting specific heat. I'm trying to find it. How come it's not there? Did I look it up wrong? Hold on, let me find it in my hard copy. I thought it's on page 38. 438. Specific heat on page 36, I beg your pardon. There we go, specific heat, it talks about it here. and that is the formula that we are just dealing with, and there they are, okay? So here, mean specific heat values of common material, constant pressure, temperature, and then so on. Okay, so the specific heat, and it's given in 2 units, in cal per gram Kelvin. I believe this would be, a chemist would be using this column. We do not use this column, guys, okay? We only use joules and kilograms, okay? So this column is, if you've taken this stuff in your chemistry class, most likely this is the column that you have been using. Anyway, so that's the column we use, kilogram in joules. So for example, specific heat for lead, 0.13 thousand, all of them 10 to the third. Mercury, 0.14, silver, 0.23, copper, 0.39, and so on, okay? Water, 4.18, and so on. You got that? So that's the table that you're going to be using. All right. Okay. So let's do example 14.6 and 14.7, and I have one more from my notes. 14.6, that's on page 37. There we go, right here. It says we will calculate the approximate amount of heat energy needed to raise the body temperature of a given amount. Okay, it says here, during a bout of the flu, an 80 kilogram man ran a fever of 2 degrees Celsius. Okay, so that means his temperature rise by 2 degrees Celsius from his original 37. Remember, 37 degree is the healthy temperature of a human being, okay? The normal temperature of a human being. I believe for a dog is around 40 or something like that. Anyway, that is, his body temperature was 39, which is equivalent to 102.2 Fahrenheit, instead of a normal 37 degree. Okay, assuming that the human body is mostly water, how much heat was required to raise his temperature by that amount? Okay, he basically wants the Q value of it. You see what I'm saying? So how do we do this problem? Simple. I hope it is. You want to keep that formula in mind, this one right here. So here we have example 14.6. So we have an 80 kilogram man, so the mass here is 80 kilogram. And then his temperature had risen. Delta T is 2 degrees Celsius. Again, once you see delta, you don't need to convert to Kelvin, okay? The delta is already taken care of, because if you convert it to Kelvin, you're going to get the same answer. As long as there is a delta, not T. In other words, if I see T equals 37 degrees, well, if you want to use that formula, if you want to use this number in a formula, you want to convert it to Kelvin. You get that? I keep saying the same thing. I hope you get that. All right. What else? And then he says he said the specific heat of this man or human is approximately equal to that of water. So we have to go back and look up specific heat for water. Previous page. It's right here. We got 4.19 times 10 to the third. You know what? I'm kind of curious to know what is the specific heat of water according to, if we get the same number for, if I use the web. Table. I just looked it up right here. It says, what is the specific heat value for water? And look at that. Check it out. It is 4.179. Our book says 4.19. See the difference? It is almost, I mean, it is relatively significant difference. So that's why you want to stick with the book. If you get this, you're probably going to get not a precise answer that is satisfying to Pearson. So always stick with the book, please. Okay, continuing on. So we have, according to our table, did I show it to you already? Yes, I did. It's right here. So we have here 4.19 times 10 to the third joule per kilogram Kelvin. Okay, and then all we need to do is this, the quantity is mc delta T, plug it in, so I got 80 kilogram, 4.19 times 10 to the third, times the difference. He gives you the difference already, 2, and all you need to do is just to calculate all of that, and then we will get 6.7 times 10 to the power of 5 joules. Okay, that's how many joules. Now, if I am curious to know, I want to know this in calories. Okay, so I go back to my conversion. So all I need to do is just put this over 1, and then I'll put the joule at the bottom because I want to eliminate it, and that's calorie right here, cal, or 1 cal that is, and 1 cal is equal to 4.186, and you just plug it in. So you have it becomes what, 6.7 times 10 to the 5th divided by 4.186, and when you calculate that, you're going to get 1.6 times 10 to the 5th calories, okay, or 160 kilocalories. Let's convert it to food calorie. Well, what is that? It's nothing but 160 food calories. Okay. And then according to the book, which is kind of interesting, he says this number, go back to the example, well, how much is 160 food calories? I'm sure a lot of you who watch their diet, it says here, okay, 160 food calories. This is roughly half the calorie intake from eating 1 ounce of milk chocolate. That's not a lot, really, but there we go. Okay, interesting. Okay, next example, 14.7. right here. It says, start from here, it says, suppose you are designing an electronic circuit element made of 23 milligram of silicon. Okay, so we have silicon, 23 milligram of silicon. The electric current through it adds energy at the rate of 7.4 milliwatt. Okay, now watt is, as you know, is a unit of power, and so that will be energy per time, so that will be joule per second. Okay, so we have a rate going on here. Rate, you know, it's given off 7.4 millijoules every second. Okay, so that's basically what it is. Okay, if your design does not allow any heat transfer out of the element, at what rate does its temperature rise? And he said that the specific heat of silicon is 705 joule per kilogram Kelvin. Okay, so how do we do something like that? In other words, let me show you what that means. Let's say I have an object, okay, and this object initially at some temperature T naught, okay, and let's say I put it, under, let's say I shine light on it, with a light from a light bulb coming, and it's given off heat. This light is given off heat, and as a result of that, the temperature of this block of, say, copper or something is rising. Okay, so in other words, it is T naught right now at T equals 0, at time equals 0, but at a later time, say 1 second, it's going to be a different number, and then another one, and so on. So it is constantly rising. The temperature is constantly rising. Why? Because let's say that the power of this light bulb, here, let's say, for example, it is 45 watt, which means it's given off 45 joules per second of energy to it. You see what I'm saying? So he's asking, if this is the power, well, how the temperature is rising? What's the rate of rising? In other words, what is delta T over delta T? That's really what he's asking for. Delta T over delta T. T here, the big T, is the temperature. So the rate of increase of temperature with time. And the way we do this problem is this. So I know that Q equals mc delta T, and he's asking for delta T over delta T per time, okay? So all you need to do is you divide both sides by time, like this. So I have Q over delta T, MC delta T over delta T. Okay, so what is Q over delta T? Well, Q over delta T is like the unit-wise, it's joule per second, and that's exactly what he gave me. Look at that. He said the electric current through it adds energy at a rate. Look at the word rate here. Rate means something per time. At the rate of 7.4 times 10 to the negative 3 joule per second. This one is nothing but the Q over delta T. You see what I'm saying? So I have that number, and he's really asking for what is delta T over delta T here. Let's continue reading it. He said, if your design doesn't allow for at what rate does its temperature increase? At what rate? What that means, rate, it means delta T over delta T. Always the word rate is you divide it by time. Okay, keep that in mind. So basically, he's really asking for this delta T over delta T right here. So I'm going to solve for it before I do anything. And that gives me 1 over MC times Q over delta T. So 1 over M here, I forgot what it is. What is he saying about? Suppose you're designing electric element. Okay, there we go. So the element has a mass of very tiny mass, 23 milligram of silicon. Okay, and he gives you the specific heat of silicon. Okay, silicon. So here I have the mass is 23 milligram times 10 to the negative 3. It becomes a gram times 10 to the negative 3 for a kilogram. You see what I'm saying? See the conversion? Divided by also the specific heat of silicon, and that's equal to, there we go, the units are fine, 705. And then on the top here, I have Q over T, which is basically nothing but that power. It's this number, 7.4 negative 3. I'm going to put it right here if you don't mind. And there we go. I just need to calculate all of that, and that'll be the answer. And when I do that, 7.4 divided by 23 point negative 3 times negative, it becomes negative 6. And then 705, answer, I got 0.46. Anybody got that? 0.46. Okay. He did it fast. Let me check what the book got. He probably did it differently. Okay. There we go. And of course, since this is delta T over delta T, so that will be, what is the unit of temperature? It's Kelvin. Remember that, see here, delta T over delta T. Well, this is the unit of Kelvin delta T per second. See that? And there we go. Okay, good. All right. Okay, the next topic, section 5, and that is phase changes. .5. Okay, what that means when we say phase changing, basically matter comes in 3 phases, at least on Earth: gas, liquid, and solid. I'm sure you know that. Well, there is a 4th one, which is the state of plasma state, which is like the plasma state is the, most of the universe is in the plasma state. You know, for example, our sun. What is the state of the sun? It's not on the liquid phase or in the gaseous phase or solid phase. It's in the plasma state. A plasma means when you have an atom that is stripped, its electrons are being stripped, which means it just you have what you call a naked atom, where you just have a nucleus without the electrons. You have a swarm of electrons that are not bound to the nuclei. So it's a mixture of nuclei and electron, but those two are not bound together. Okay, it's an extreme state. We can do it in the lab, in advanced labs here on Earth, but it's not a normal state on Earth. You find it at this, at the core of stars, for example. This is the plasma state, and it is considered a fourth state. But we don't deal with it here in our course. Okay. So anyway, so we want to. As far as we are concerned, there are three states of matter. It is gas, liquid, and solid, of course. Okay. And please take the time to read the first page at least about phases, right? Let me go to that page, 38, next page. Talks about different phases of matter, and so this one right here. It is really important stuff, and especially what is L. I'm going to talk about L sub F and L sub V right here. He gives you a lot of details about those. We're going to be dealing with them in a minute. Okay, what is called the latent heat of fusion and the latent heat of vaporization. Okay. Okay, so what's going on here? First of all, which is responsible for the change of phase or to be in a specific phase? And that is, it is heat and temperature. So heat and temperature are responsible for phase change. I'm sure you already know that. Okay. So we have two concepts here. One is called two phases or two transitions. One is called fusion, which basically fusion is just a fancy word for melting. Okay, this is the word we use in daily language, melting. So, for example, ice melting into water. Okay, that's called fusion. Okay, and then of course we have evaporation. What is evaporation? Evaporation is basically steam, for example, right? An example of evaporation is something turning into steam. So it is from water into vapor or steam. Okay. So now we define what we call the latent heat of fusion. Okay, the word latent means like hidden. Okay, the latent heat of fusion is basically Q, which is the energy given or energy taken, is equal to Q equals M, the mass, times L sub F. Now, what is L sub F? L sub F is a coefficient that you can actually look up in the book or in a table, and it is shown on page 39. Let me just show it to you very quickly. Right here, it's kind of a messy table right here. All you care about, this stuff right here says the normal melting point. This column and this column may not be important to you, okay? You don't need those. All you need is the latent heat of fusion, L sub S, right here. And then I'll talk about the latent heat of vaporization, okay? It's right here. Okay, the others, those just kind of messy. We really don't need them. So you can ignore normal boiling point and normal melting point. And what counts is the three columns: the substance, latent heat of fusion, latent heat of vaporization. So for example, nitrogen. What is the latent heat of fusion? 25.5 times 10 to the third. I'll come to explain it in a second. Just give me a minute. The latent heat of vaporization for nitrogen is 201 times 10 to the third. Say, for example, lead. Latent heat of fusion, 24.5 times 10 to the third. Vaporization, 871 times 10 to the third, and so on. You got that? You get silver, gold, copper, sulfur, and water, and so on, okay? Those are the three columns that you need. All right. What does that mean? Okay. Let's say, for example, I have ice, okay? I have a piece of ice. I take it out of the freezer. It's ice, and I put it on the table. Or let's say I put it in a cup. Let's say I put a bunch of ice cubes in a cup. And after a while, or let's say I have let's say you have a thermometer in it, and it's reading 0, okay? Just reading 0 degree Celsius, because that's just the freezing temperature of water. After a while, the ice will begin to melt, right? And while it is melting, and let's say half the ice now, half the content is ice and the other half is water, if I would look at the thermometer, I will find it to read still 0, okay? This 0, why is it 0? Because you have a mixture of both, okay? And in order for you to get all of it liquid, okay, liquid state, you have to wait long enough until the temperature rising, okay? But right at 0, it is freezing and liquid at the same time, or it's a mixture of the two, okay? So at that stage, at the 0 point, it's where the phase happens, the phase change happen. You could have from ice melting into liquid, or you can have liquid melting into ice. I mean, let's take the converse. Let's say I have a cup of water, and then I put it in the freezer, and I have inside a thermometer inside of it. And let's say that while it's in the freezer, I can find a way to monitor the thermometer. So what's going to happen here? When it reaches 0 and I look at the water, it's going to be a mixture of ice and water, okay? So in other words, when does the phase change happen? At the 0 temperature of water, okay? The same thing is happening with, let's say I have water and I have the thermometer and I put it on the stove, okay? And I wait for it until it starts to boil. Okay. Now, while it is boiling, I look at the temperature. It's 100 degrees Celsius because this is the boiling temperature of water. At the same time, this water is slowly converting into steam, vapor. You see what I'm saying? So this is that temperature, 100 degrees for water, is where the phase change happens. Okay. So the latent heat of fusion is basically at that 0 degree where you need energy to make the water melt from ice to water. You make the ice melt from ice to water. And the latent heat of vaporization which is Q equals mL sub V, is how much energy do you need to make that phase change from liquid to solid, okay? So basically this one, it tells you how much energy do I need to transition from liquid, from ice to liquid, or even from liquid to ice. I mean, it's the converse is also true. It goes in both directions, okay? So it goes from here for the fusion, it's melting. Melting means from ice to water, and it's the same amount of energy you need for water into ice, okay? Either direction is fine, okay? And for vaporization is from water into steam, or maybe I can collect that steam and liquefy it, or from steam into water. And you get the same. So both of them, so this would work for both of them, okay? So the Q here is basically how much energy do I need to transition from one phase to another. You get that? Okay. I'm going to give you an example, I promise, in a minute. But let me move on to the next topic, and I'll come back to this. and that is colorimetry, which is section 14.6, colorimetry. What colorimetry means is the following. Let's say, for example, I have, and this is an experiment that you guys will do this semester about colorimetry. The experiment pertains, I'm not going to give you the whole experiment, but it's simply like this. Imagine I have a cup of water or a beaker. Okay, there's some water in here. Let's say tap water. Sorry. Okay, and let's say that the temperature of this water is T0, okay, whatever it is. And then on the side here, I am heating a small block of lead, or let's say copper, any metal object. Okay, so here it is. It's a little block here. I'm heating it up, and it is really hot. Okay, this thing is really hot. And then I grab it with tongs or something, and then I dump it in here. Okay, and now it is here. Now remember, I have a thermometer. Is right there. This is the thermometer, and it is measuring the temperature. So initially, before I threw the block, the temperature reads T0. The temperature reads T0. And now when I throw the block in there, so of course the temperature is going to increase. Increase to what? To something else. Let's say T1, whatever it is, okay? Or let's say, T final, whatever. Okay, so what happens here? Well, what happened? This is called colorimetry. Basically, what happened is that when I put the hot block or cube of copper in there, part of that heat was given off to the water, right? So part of that heat was given off to the water. As a result of that, the water's temperature starts rising, okay? And what happened to the temperature of the block? Start decreasing, okay? And so the temperature of the block kept decreasing, and the temperature of the water kept increasing until both became at what we call thermal equilibrium. We both have the same temperature. You see what I'm saying? So basically what happened is that I started with T0 for water, and let's say that the temperature of the block, let's call it T1, okay? And so I started at T0 for water. After a while, I ended up with temperature final, I'm going to call it TF, okay? And what happened to the block, it started with T1, and now it is at temperature TF as well, because thermal equilibrium. You see what I'm saying? So what happened here is that there has been a Q value that is lost by the block given to the water. Make sense? And then there is another Q value gained by the water, lost by the block, correct? Make sense? Well, how those two Q's are related? They must be equal, right? You see what I'm saying? It's like, think of it this way. Let's say you and me are in front of each other. You don't have any money in your pocket. I have $10 in my pocket, $10 bills in my pocket. Okay? And what I'm going to do, I'm going to give you $2. Okay, I'm going to give you $2. So what happened? Now you have $2. You have gained $2, and I have lost $2. In other words, the amount of gain is equal to the amount of lost. That's what's important. So Q gain equals Q lost. This is very important relation. Your book doesn't talk about it this way. It explains this in a very different way, but I like it this way. So let me go back to this. So here the Q is lost by the block because it's hot, given to the water. That amount of loss is equal to the gain in water, gained by the water, lost to the block. You got that? In other words, we say the following. So Q gain is lost, so it becomes remember that Q is equal to MC delta T, so it becomes For gain, who gained? Water gained, right? So the water gained, that's going to be M for water, whatever the amount of water that we're dealing with, times the specific heat for water, times delta T for water. Remember, we started at T naught. We started at T naught and then TF. And always subtract the two in such a way that you'll get a positive number. So it's going to be TF minus T naught, correct? And that's equal to the Q lost by the block, so that's going to be the mass for copper, times specific heat of copper, I can look it up, times delta T. What is delta T in this case for the copper? Is, which one is greater? The T1 is greater, so it's going to be T1 minus TF. You always subtract in such a way that both will be positive, or the result is positive. And there we go. That's the formula that I can deal with. This is the essence of colorimetry, okay? I'll give you an example, a real example with numbers. And that's example, is it in the book? I have one. I'm not sure if it's in the book. Nope, it's in for my notes. It's not here. No, it's right here. I'm sorry. It's example 14.8. I'll show it to you. Page 42. It says that this example involves heat flow between liquid and its container. Okay, it says a Turkish restaurant serves coffee in copper mugs, okay, with the inside tin plated to avoid copper poisoning. Okay, a waiter fills a cup having a mass of 0.1 kilogram. So this is the mass of the cup. It's a copper cup. And initially at 20 degrees Celsius, which is almost room temperature, with 0.3 kilogram coffee that is initially excuse me, at 70 degree temperature, 70 degrees Celsius. Okay, what is the final temperature after the coffee and the cup attain thermal equilibrium? All right, assume that the coffee has the same specific heat as the water and there is no heat exchange with the surround. Okay, so the way he does it, he kind of add them up together and then he put it to zero. I like to say that the heat gained by the copper is equal to the heat lost by the coffee. See what I'm saying? I like it that way rather than adding and equal to zero. That's just my way. So I'm going to do it my way. I hope you'll find it more interesting. Anyway, let me write down the data. So here it says here we have a Turkish restaurant. And we have a copper mug. And the cup and the coffee. For the cup, he says the mass of the cup is 0.1 kilogram, and the initial temperature of the cup is 20 degrees Celsius. That's, at room temperature. Coffee is hot. The mass of the coffee is 0.3 kilogram. Actually, that's a lot of coffee. And the temperature of it is 70 degrees Celsius. Okay. So what happened now? Here is the cup. Right, and the cup is with this mass and the temperature. Now you pour the coffee in there, and if you wait long enough, it's going to reach thermal equilibrium. So I'm going to say that heat gain equals heat loss equal heat loss. Heat gain equal heat loss. Who gained the heat? Who gained the heat? The cup. The cup is cold. Okay, who lost the heat? The coffee. Okay, you have to ask those questions like that, loud. Okay, all right. So both of them, MC delta T. MC delta T for the cup equals MC delta T for the coffee. Coffee lost the heat. You see what I'm saying? All right, you just build it up slowly. Okay. Now let's plug in. What's the mass of the cup? 0.1. Do you see it right there, up there? Specific heat, well, it says it's equal to water. I'm sorry, this is for this is for the cup, which is copper. So I need to look up the specific heat for copper, and when we look it up, I can see it. It's right here. Okay, it says it is 390. Okay, you can go back to the table and look it up, but let's say it's 390 right here. So I'm going to go 390 times the temperature. Now this is where it gets a little bit tricky. Keep in mind, it's not necessarily, here, let me write it down here. It's not T2 minus T1 or T1 minus T2. It is one of them in such a way that it have to be positive. This is important. It have to be, in other words, you put the hot minus the cold. If you put the cold minus the hot, you're going to get negative number. You see what I'm saying? So you always put, you subtract them in such a way that you always get a positive value. Okay, so now the cup was cold. Look at that. The cup is cold, and then it gained heat, so it became hot. So the hot is higher, so that's going to be T final minus 20. You see what I'm saying? I hope you understand that. Now let's come to the coffee. The mass, I'm sorry, oh, this is correct. I'm sorry, this is fine. Okay, now we have the mass of the coffee is 0.3. And the specific heat of coffee is that equal to water. That's what he told us. So this is 4190 times what? The difference in temperature. Again, coffee was very hot, so we're starting with 70 minus T final. You see the difference between the two guys? Make sure you understand this one and this one. You're going to subtract in such a way you're going to get a positive answer. You got it? This is important. Okay, and there we go. And the rest is easy. All I need to do is to do the algebra to solve for TF. And those two. You see what I'm saying? Just some, there is some amount of algebra involved here. And when you work it out, I mean, I have it almost, I have worked it out on my sheet here. Let's do maybe a couple of steps. So here, 0.1 times, I'm right here. So that's going to be 39 TF minus 20 equals to 0.3 times 4190 is 1257 times 70 minus TF. You see what I'm saying? And then you multiply this here and here, and you multiply this here and here, and so on. And when you work it out, I am going to get the following. With a couple of steps down, I'm going to get this. TF minus 20 equals to minus 32.2 TF plus 2256.2. Okay? And then you work it out, you collect the TFs together, and you'll end up with TF equals to 68.5 degrees Celsius. Okay? Okay, good. So let me just make a little note here to remind you. When you are plugging, is it TF minus 20 or 20 minus TF or 70 minus TF or TF minus 70? You keep in mind this is the rule. Okay? That's the rule. So you swap them according in such a way that you're going to get a difference that is positive. Got it? Okay. All right, here's another example for colorimetry. And I'm going to be emphasizing those kind of problems on the homework and on the exam. So please make sure you understand them. Here's another example, and I believe this is from my notes. Yes, it is. So we have a metal ingot. 0.05 kilogram is heated to 200 degrees Celsius, then dropped into a beaker containing 0.4 kilogram of water at 20 degrees Celsius. Okay, this is similar to the experiment that we'll be doing. Now, if the final temperature of the mix is 22.4 degrees Celsius, okay, what is, I'm writing too fast, what is the specific heat of the metal? Remember I told you the specific heat is unique for any substance, so we can actually identify the metal from that specific heat. Okay. All right. So how do we do this problem? Similar to what we've done. So basically, what you have a beaker. There is water. We are ignoring the specific heat of the beaker, I guess. In the experiment, that you don't ignore the specific heat of the experiment that you'll be doing. Anyway, and then I'm going to put a metal piece in there, and as a result of that, there will be heat gained by the water, and it is lost by the metal, and then you'll reach an equilibrium. The equilibrium is given to us, the temperature, and now he's asking what is the specific heat of the metal. Okay, as a matter of fact, those kind of experiments are done specifically to find the nature of the metal. You see what I'm saying? Okay, or to verify if it's a pure metal or not. Anyway, so how do we do it? Well, just like I told you, I like the idea of saying Q, heat gained, is equal to heat loss. Okay? Less by who? Who lost? The metal. I want to remind myself. And who gained? The water. Got it? So that will be MC delta T, water, equals MC delta T, metal. Got it? Okay. And then we just build it up. So we have for the water, he said containing, let's go back to the table, to the what's given to us. He said the metal is 0.05 kilogram, and at 200 degrees, dropped into a beaker of containing water, 0.4 kilogram for water at 20 degrees. Those are the numbers that we need. So the mass of the water is 0.4. Specific heat of the water, we already know what it is, 4190. Now the delta T. Well, how do we do the delta T? The water gained heat, therefore the final is greater than the initial, so that's like that. I know he gives us a final, but I want to write it that like this just to make sure that you understand what I'm doing. Equals to, now the mass of the metal is 0.05 times the specific heat of the metal. This is what we're looking for. And delta T, it lost, so that means it started with 200 degrees Celsius. This is what he said, look. He said heated to 200 degrees Celsius, and what happened to it? It cooled off, so it lost. So it's going to be 200 minus the final. The final is what? Is right here, 22.4. Let me just call it T final. And then all we need to do now is just plug in the T final and then solve for C. This is really an easy problem becomes. So 0.4, 4190, and then 22.4, I'm sorry, yeah, that's right. Minus 20 equals to 0.05 C, excuse me, times 200 minus 22.4, and then the rest is algebra, right? You just kind of work it out. You can get a number out of the left-hand side, just one number, and then you get a number here, multiply by 0.05, and then you solve for C, and then when you work it out, C becomes equal to 453 joule per kilogram Kelvin. And then when you look it up, I looked it up, and it is about iron. It kind of mimics iron or similar, or iron alloy or whatever, but it's close to iron. Okay, good. One more problem. I have two more problems. We'll be done with this chapter. Okay, one more example. This is kind of a nice example. I have it for my notes. kind of a comprehensive example. Okay, imagine that I have, let's say, a cube of ice, okay? So what I want to do, I want to take this cube of ice and I want to heat it up until I'm going to heat it up until it converts from ice to water, and then from water to boiling water, and then from boiling water to steam. And all of it going to be just totally steam, and then super steam at temperature 120 degrees, okay? The question is, what is the total energy that I need to convert this cube of ice from ice at 0 degrees to steam at 120 degrees? Not just 100 degrees, 120, to really, really hot steam, okay? How much energy do I need? You got that? So there are a lot of steps going on here. Okay, so let me write down the statement of the problem. It says how much heat is required to convert 1 gram, okay, just 1 gram, 1 gram block of ice at negative 30 degrees Celsius, not 0, sorry, negative 30 degrees Celsius to steam at 120 degrees Celsius. What is the total energy needed, okay? Now, this kind of equation, or this kind of problem, we can't do it in one step. We have to go steps. The first step is that I want to go, how much heat do I need to convert from minus 30 to 0 degree? And then from that 0 degree, it's still ice, but it's gonna melt, so that's gonna be a transition. So that's a heat of fusion. So I need a phase change. And then from there, from 0 to 100, and from 100 to 100, which is the phase change again. So that's I need a heat of vaporization, and then from 100 to 120. So there are a total of 5 steps. Let me list them for you before I do the problem. Here it is. The first step, step number 1, it is from negative 30 degrees Celsius to 0 degrees Celsius. And the formula that I will be using for that is basically Q equals mc delta T, where C here for ice. I need to look up the specific heat for ice. It's different from water, okay? So that's the first one. The second one is from 0 degrees to 0 degrees, 0 degrees to 0 degrees. This is phase change. And in this case, since it is 0 to 0, that is melting. Okay, I'm doing melting here, or fusion, right? All these words, same thing. So that means Q in this case is going to be ML sub F. You see what I'm saying? Because here I have, when we say melting or phase change, here I have ice, water, mixture, at 0 degrees. You see what I'm saying? Okay, the third one is from 0 degrees to 100 degrees, and that basically, here this is a liquid, and it's nothing but Q equals mc delta T, but this C is really for water, liquid water that is. You see what I'm saying? And then the fourth step is from 100 degrees all the way to what? 100 degrees. It's nothing but a phase change here. So this is phase change as well. It's steam or vapor, whatever you want to call it. And it is Q equals ML sub V, latent heat of vaporization. We'll come back to it in a sec. Again, you have a mixture here of steam. Here you can say that it is liquid steam mixture. Okay? And then the last step is from 100 degrees Celsius all the way to 100, what is it? Well, I forgot what it is. Until 120 right there, right? So this is 100 degrees Celsius to 120 degrees Celsius, and it's basically, this is all steam, but there is no phase change. So it's just basically Q equals mc delta T. This is for steam here, or vapor. Okay, I have to look up the table to get that number. Okay, so that's basically the, so keep in mind, we use this formula, mc delta T, just how much heat added. When we deal with phase change, we have to use this one, Q equals, and usually those Q, the phase change is actually a very large number. You'll notice in a minute. Okay, so let's get down to it. All right, let's work on it. So the first step is Q equals mc ice delta T. He said, let's write down what's given to us. Here, he said how much heat is required to convert 1 gram. So the mass here is 10 to the negative 3 kilogram, right? Of ice at negative 30 to 120, all right? So here I have the mass. Here, let me just write down the mass here. 10 to the negative 3 kilogram. Initial temperature, of course, is negative 30 degrees Celsius. And the final temperature is 120 degrees Celsius. This is final, okay? This is the data that he gives us. All right, let's start with the transition from, I hope you've written all of the above. Please write them down before you go any further, because I'm not gonna be switching those two pages. So, okay, so we have here, trying to erase the equal sign, if I can do that. It won't erase. There we go. Okay, so the first one is from negative 30 degrees Celsius to 0 degrees Celsius. And that will be 10 to the negative 3. And then specific heat of ice is 2090. Look it up. And then delta T. Remember, delta T have to be a positive number. So what is it? Well, we're starting from basically the difference between them, and make sure it's positive. So just basically 30 minus 0. Or if you want, hold on, here's another way of doing it. This one doesn't erase anymore. There we go. 0 minus 30. Instead of saying it, that'll be 30 there. And when you calculate that, it's going to be 62.7 joule. Okay? That's the first one. We're going to call it Q1. Okay? The second step, again, I hope you have your notes beside you. The second step is phase transition. Okay? From 0 to 0, that's phase transition. Phase change, excuse me. And that will be phase change. Q2 is equal to ML sub F. Okay? L sub F is what? Is the phase change for water. So let me go back to the table. Let me just show you at least one of them. And it is on page, let me look it up here, on page 39. And that's from ice to ice. So maybe it's not there. And because this problem is outside the book, maybe I don't have ice here. Oh, well, okay. So there is water. It's right here, but there is no ice. Anyway, again, because this problem is from my notes and I got it from outside your textbook. So let's just assume that we can find it. Trust me, I will make things available for you. If you're doing homework or something, all of that will be available for you. But anyway, so let's just suppose that we have it. So for LF for ice, I'm surprised that it's not there, actually. It's kind of strange how that is. Anyway, for LF for ice is 3.33 times 10 to the negative 5, okay? Times, I'm sorry, to the positive 5. Okay, and then we just plug it in. So we have Q2 is equal to the mass is 10 to the negative 3 kilogram times 3.33 times 10 to the 5th. And then we plug it in, you end up with 333 joule. Okay, so that's Q2. Got it? And number 3, which is we are transitioning from 0 degree liquid water to 100 degree liquid water. Okay, so that will be Q3, which is MC delta T, where C here is the liquid water. We know what the number is. And so in this case, it's going to be 10 to the negative 3 times 4190 times 100 minus 0. Again, you just need to calculate that. Oh, let me put it here. And when you calculate that, you're going to get 419, okay? My erase is not working well. Anyway, there we go. So that's 419 joule, okay? And then the fourth one, which is, again, this is a phase change again. So that will be Q4 is mL sub V, V here for vapor, water vapor, and the mass is 10 to the negative 3. And I have it from my notes. It is 2.26 times 10 to the 6, and then I multiply, I calculate that, it becomes 2,260 joule. As you can see, the numbers for phase change is large, okay? And the reason is for that is because of the bonding of molecules. You know, it needs a lot of energy to bond the molecules or to unbind, to disintegrate them or to break them apart. It takes up a lot of energy, that's why. Okay, so anyway, so we have Q4 is that, and then the last one, Q5, which is basically what, from 100 to 120, and we're talking here steam, so it's going to be Q to sub 5 is MC delta T. This is for steam here, sub S, and then the mass is 10 to the negative 3. For steam is 2.01 times 10 to the third, and multiply this by 120 minus 100, and then we can calculate that, and that will be equal to 40.2 joule. Okay, that's Q5. So what is, so therefore, the total amount of heat needed is what? You just add them up together, total. So that's going to be Q total is Q1 plus Q2 plus Q3 plus Q4, oops, plus Q5. Or you can put it in summation notation if you are mathematically inclined. And then you just add them together. So when you add up those numbers, it's going to be 62.7 plus 333 plus 419 plus 2260 plus 40.2, and you add them up together, it becomes 31,140. I'm sorry, 3,114.9 joule. And there we go. That's the Q total. And there we go. Okay. I hope this is clear. Let me go back to the book because I'm kind of bothered by the fact that it's not giving you ice and all that. Let me just go back one more page. I hope it's written somewhere. Oh, it's probably one more. For water, because he talks about water here. There we go. Here, okay, tell us the whole again. Changing. Okay, boiling, evaporation. The corresponding heat per unit mass of cold air is heat. The normal atmospheric latent heat for water. There we go. Okay, so for water is right here, 2.26 times 10 to the 6, and that's exactly the number I used in my notes. And then for latent heat for fusion, melting of water, 3.34. Again, I use 3.33 because I got it from a different table, not from your book. But if we are sticking with our book, it would be 3.34 times 10 to the 5th. I use 3.33 times 10 to the 5th. Again, I used a different table. But anyway, there we go. Okay, so he has them here, but he doesn't have them on the table, which is kind of silly, but anyway. All right, the very last topic that I have, I only got 15 minutes for the 2-hour mark, and that is the last topic in the chapter. It's a very simple topic, and it's called heat transfer. And the one that you want to care about is how heat transfers through, I'm trying to find it, how heat transfer through a thickness of a wall, okay? Let me go over it. I think I can finish it in 10 minutes. It's not a difficult topic. Heat transfer. Specifically, go to example 14.10. Read section 14.7, page 443. Okay, heat transfer. Okay, so I'm going to go over it very quickly. You read the section, I hope, and then you may want to come back and read and look at the example that I've done. Okay, so specifically, I'm talking about transfer by conduction. There are three kinds of heat transfer: conduction, convection, and radiation. We are going to concentrate only on the conduction part. Basically says the following. Let's suppose I have, let's say I have a wall. Okay, here is the wall, and it has a certain thickness. I'm trying to draw it 3D as much as I can. There we go. Okay, and let's say that this side of the wall is outside, outside, and this is inside your room or whatever, okay? This is inside your house, okay? And let's say outside is cold and inside is, well, let's say hot. We'll just use the term hot, okay? And the temperature outside is T1 and the temperature inside is T2, okay? So what will happen, because inside is hot, so what's going to happen, part of that heat is going to radiate or going to go through the thickness of the wall like that, and it will heat. The word I'm looking for is flow. Part of the heat is going to flow through the thickness of the wall, and then it'll come out on the other side. Okay? And the question is, what is the rate of heat flow? We are interested in this heat flow. So, rate of heat flow, which is basically delta Q over delta T. Your book uses H, capital letter H for that delta Q. So he calls it H. I don't care for that symbol, but he calls it H, capital letter H. I think from chemists, enthalpy, I think they call it in chemistry, whatever. Okay, and it basically, this delta Q over delta T is equal to K times A times T2 minus T1 divided by L. So what does that mean? Well, A is the area of the wall. We are assuming both areas are the same, okay? So it's the area of the wall. So A is the area of the wall. L is the thickness of the wall. It's basically here, this one. Okay, and what else? T2, T1 is basically the difference in the two temperatures, hot and cold. Okay, you want to make it positive if you want to. I mean, this one is not, you don't need to, you can relax that rule. But, you may want to make it positive. And then K here is it's called the conductivity or the thermal conductivity coefficient. Again, we have another table for that. We have a lot of tables this chapter, and it should be there. Let me show it to you very quickly. On page 45, right, here's a good example that you want to read. I'm using a different example, but anyway, next page, is it? Thermal conductivity, sorry, the previous page. There we go. K, thermal conductivity coefficients. There's a bunch of them here. For example, for lead, 34.7, steel, and so on. Okay, there we are. For solid and so on. Okay, and that's about it. So let me give you a quick example that I can do in 5 minutes or so. It says here it says find the amount of heat transferred in 1 hour. In 1 hour by conduction through concrete wall. So we have a concrete. Through a concrete wall, I have to look up thermal conductivity for concrete. That is 2 meters high, 3.65 meters long, and 0.2 meter thick. Okay. If one side of the wall is held at, so one side of the wall is held as 20 degrees Celsius and the other is held at 5 degrees Celsius. Okay. I hope this sounds like not a difficult problem. So all I need to do is I take this formula right here, and because he wants the heat transfer, he wants really Q, and he doesn't want the T. The T is given to me, so I can just put it here, cross multiply it. So basically what the formula would look like is this. Q equals to Ka T2 minus T1 over L times delta T. Of course, delta T here, he said 1 hour, right? So that's 3,600 second. And then T2 minus T1, so that will be is 20 minus 5, and that will be 15 degrees. Again, just subtracting in such a way to be positive. You see what I'm saying? Of course, the thickness, he said, is 0.2 meters. And then the area, well, he says it is 2 meters high by 3.65 meters long. So that's basically the area. So it is 2 by 3.65. And then you work out that number. And then you just plug in everything in there. Oh, sorry. And then, of course, the coefficient for concrete, let me look it up for you very quickly. I hope it's here. There we go, 0.8. And I use, okay, so we have the same number, 0.8. And then you just plug in everything in there. And then once you calculate that, so that's 0.8 times 2 times 3.65 times the delta T, let me just put delta T here, 3,600 times 20 minus 5 over 0.2, and then you just work it out, and I got 1.6 times 10 to the 6 joule. Okay, that's all. I'm not going to give you something tougher than that when it comes to the conduction. Just be familiar with this equation and how to use it, and that should be good enough. Okay, and that's it for the chapter. I think I covered everything we wanted to cover. So let me know if you have any questions. Goodbye.